Hi! In the previous two videos, we've learned quite a bit about calculating integrals. But as you might have noticed by now, calculating integrals is a little bit more tricky than it is in case of derivatives, where usually calculation is very straightforward. We just need to apply some specific combination of rules, and it usually doesn't even matter in which order we are doing it. With integrals, it is way more tricky, and one of the reasons why it is so tricky is because in case of integrals, we don't have product rule and we don't have quotient. But we have a counterpart of a chain rule that we are going to use today. And we're going to start in this video learning how a technique called integration by substitution. Okay, so look, we have a situation in which we have some function, let's just say y equals g of x. And look, let's just say that this function is very complicated in a sense that it's really hard to, or maybe even impossible, to integrate it using the rules we've already discussed. Now, very often in such circumstances, what we can do is to actually do what we did in the case of the chain rule. So introduce an auxiliary variable. So we can, for example, if here we have a situation that x influences y, but this relationship through function g is very complicated, we might introduce addition, this auxiliary variable u, and examine the integral step by step. Very often this comes extremely handy, because look, if it happens to be that we can express integral of some g of x dx as some function of u multiplied by derivative du dx, of course dx at the end. Look what is happening over here. Those two dx's are cancelling each other out. So what we are obtaining as a result is an integral of f of u du. And look, here, what we actually, the only thing we need to have is to integrate this new function. So as a result, we will obtain integral of this function, of course, plus some c. Okay, and look, it's really to understand how does it work. Because look, if I'm having some function f of u, and I'm going to differentiate it with respect to x, I need to use the chain rule. Look, I can write it simply as derivative with respect to x of the function f u. But look, if I want to differentiate it, I also need to know what is the relationship between u and x. If there's none, this is going to be always equal to 0. But if there is some relationship, and we are establishing this relationship on our own by introducing this auxiliary variable, I can use the chain rule to calculate du f of u and multiplying it by du dx. Look, we still see that this must be true because those two are cancelling each other out, and we are ending up with this expression. And look, basically what we get out of this is derivative of f of u with respect to u multiplied by derivative of u with respect to x. And of course this, in other words, is f of u. Remember, because we are using now capital letters for primitive function, this is derived or derivative function. times du dx. And look, basically, what we've shown over here is that if I'm going to have this somewhere inside the function, I can transform this into this expression, right? And look, this is what we see over here. This is our f of u, the same as it's here, but not differentiated. And we are transforming it into this. And look, what is the only difference? We are multiplying here by dx. Here, we are dividing by dx, right? So this is why here we are just getting f of u out of this entire expression. And this is why this expression is missing this dx at the end, right? Because we divided by dx. Which actually shows that by introducing this auxiliary variable on the condition that we're going to have a derivative of this variable in front of it, we will be able to calculate the integral. Okay, so this is, let's just say, so here we see the rule, and we see the proof that this rule must actually work. But the best way to understand it is to see a couple of examples. So let me show. And let's start with something rather trivial. We've got integral of 2x times x squared plus 1 dx. Okay, look, again, in this case, we could just multiply everything out inside the integral and do it in an easy way. But let's start by analyzing this case because it's very simple and it's easy to understand. Look, first thing that we do is that we need to recognize what is the most problematic component and express it as u. Look, in this case, this is clearly going to be expression in parentheses. So let's just say that u is equal to x squared plus 1. Now, how much is du dx? Well, if I differentiate this expression with respect to x, I'm going to get 2x. Okay, so what can I do now? Look, instead of 2x, I can write du dx. And instead of this expression, I can write u. And I finish with dx. Okay, and look, what is happening? Now, those two dx's are canceling each other out, and we are getting expression. The order in which they appear is irrelevant. But I changed the order so it looks nice. And look, here is an extremely easy function to integrate. Because integral of u with respect to u is going to be u squared over 2 plus c. The only one thing we need to do at the very end is to substitute back for our u. So we get that this is x squared plus 1 squared over 2 plus c. And it's ready. Okay, so I hope you can now see more or less the mechanics of it. So now let's move to a case that is slightly more involved, but not by much. Okay, and our example is integral of 6x squared times x to the power 3 plus 2 to the power 99 dx. Okay, so again, first we need to recognize what is the most problematic expression. And again, now it's going to be, again, expression in parentheses. But look, what is the difference between this and the previous example? In the previous example, we could actually multiply everything out. Could we do it here? Look, would you be willing to multiply this 99 times and then multiply this by 6x squared? Well, I assume definitely not. And as you will see in a second, this integral is trivial in calculation. Okay, so our u is going to be x cubed plus 2. Okay, then du dx, so derivative of u with respect to x is 3x squared. Do we have it over here? No. So this is problematic. Can we deal with this? Of course. Look, we need to use the rule about integral of the multiple, and we know that we can take out of the integral any constant. I want to have 3x squared here, so I'm going to take 2. And I got 3x squared times x cubed plus 2 to the power 99 dx. Okay, so what can we do now? Look, now the case becomes trivial. All we need to do is to substitute. So we get that this is 2 times integral of du dx times u to the power 99 dx. And again, two dx's are cancelling each other out, and what we get as a result is integral of u to the power of 99 with respect to u. Okay, and again, this integral is extremely easy to calculate. This is simply u to the power 100 divided by 100 plus c. Okay, so out of this, we are getting that this is u to the power of 100 divided by 50 plus c. And now, all we gotta do is again to substitute back for u. So we get that our outcome is x cubed plus 2 to the power of 100 divided by 50 plus c. Okay, I hope you were getting the hang of it. So let's try again, and let's try something even more complicated than the one we did just now. Okay, so let's just say that integral we need to calculate right now is 8x cubed plus 4 times x to the power of 4 plus 2x to the power of 49 dx. Okay, again we see that straight multiplication is no way to go, too much to multiply. So we definitely need to introduce our auxiliary variable u. Okay, so what should be our u now? Well, clearly, this is the expression with the power of 49 with which we would have the most issues. So, x to the power of 4 plus 2x. Okay, so now I'm calculating derivative du dx. This is just 4x cubed plus 2. And again, I'm looking if this is what I have over here. Well, clearly not. Can I do something with this expression so it won't take this form? Again, the trick is very simple. I just need to take 2 out of this entire parenthesis. So I'm getting that this is 2 times 4x cubed plus 2 times x to the power of 4 plus 2x to the power of 49 dx. And now, as you see, the only thing left we've got is substitution. So we've got 2 integral, integral sign, and now instead of this I can write du dx instead of this, I can write u to the power 49 dx. And look, I get that this is 2 times. Those two cancel each other out. Again, u to the power 49 du. And now I'm integrating the simpler function with respect to u, which again is a rather trivial task. So we get that this is 2 times u to the power of 50 divided by 50 plus c, or u to the power of 50 divided by 25 plus c. And again, the only thing left we have to do is to substitute back for u, and we receive the answer that this is x to the power of 4 plus 2x to the power of 50 divided by 25 plus c. Okay, and look, this is it. This is how integration by substitution works, and this is also how we use it. So the only thing left for you is to practice and just do a lot of exercises using this rule. Thank you for your attention and see you in the next video.